Hi students, now we are going to discuss the vertical oscillations of a spring mass system. So in the first picture you can see a spring is held in the vertical position along the y-axis. There is no mass at its bottom, so the spring will not be stretched. In the second picture you can see a load is attached. Okay, this is the mass M. The load is the wooden block of mass M. When it is suspended at the bottom end of the spring is getting stretched. That is, the length of the spring elongates, increases. So you look at the second picture with respect to the initial position called the mean position. This is the resting position. From here, now the mass is stretched through an extension L. So L is called the extension. Okay, the distance between the previous position and the new position, that is L. Now this is like suspending a mass below the spring balance. Okay, when you attach any mass in the spring balance and when the mass is left undisturbed, what will happen? It will just go down and it will be at resting position only. So that is the second position. It is in equilibrium. It is at rest. So in the second picture, you must understand that the spring and the mass together are in equilibrium. That is static equilibrium. Both are at rest. So there is no acceleration for the mass. Okay, acceleration in this middle picture is equal to 0. Okay, now what are all the forces acting on the system? Let us see in the second picture. The weight of the wooden block corresponding to a mass M is mg. In which direction is the weight of the wooden block acting? It is in the vertically downward direction. That is the force. Okay, force acting in the vertically downward direction is the weight of the block mg. Okay, suppose if you remove the load again, the spring has to go back to its original position. Which force is responsible for that is called the restoring force, which is otherwise called as restoring force. So I have shown in the second picture, the restoring force is developed in the spring in a direction opposite to that of the weight. Is it not? So I have indicated by F1. Okay, F1 is equal to minus KL. So there are two forces acting on the spring mass system. What are the two forces in the second picture? One is the weight of the block, that is mg in the downward direction, and the restoring force F1 is equal to minus KL in the upward direction. So under the action of these two forces, the body is not gaining any acceleration. So what must be the net force is equal to 0. So mathematically I am going to write below this diagram. Okay children. So in the second picture, the weight mg, okay, minus KL, mg minus KL is equal to mass into acceleration. So mass is m, acceleration is 0. So this is equal to 0. Understand that? So I can shift this minus KL to the right hand side. So I will write mg is also equal to KL, or this m divided by k, m divided by k is equal to L divided by G. So this is the first equation. So based on the second picture, we have derived an equation m by k is also equal to L by G. Have you all understood first? Okay. Now in the second picture, when the wooden block is pulled down further, when it is pulled down further and released, what will happen? Now only the spring mass system will oscillate up and down. So in the third picture you see it oscillates. Understand? So the acceleration is not equal to 0. The wooden block and the spring system will now have an acceleration, and that acceleration is not equal to 0. Understand children? Okay. So here the net force must be equal to mass into acceleration. That's all. Okay. In the previous picture, the net force is equal to 0 because acceleration was equal to 0. But in the third picture, the net force acting on the system. What are all the forces? Let us see now. So in the third picture, the first force acting in the downward direction is the weight of the wooden block. Okay. So M into G in the downward direction. Then the restoring force in this case will be different than the previous case. What will be the restoring forces now? F2. And this restoring force is this time minus K times L plus Y. What is Y here? Y is this further extension, or this is only called as a displacement. Understand? So L already it has extended. Beyond this, by how much is the displacement in the y-axis? The displacement in the vertical direction is denoted by y. Therefore, with respect to the initial first position, totally now here it is L plus y. Okay. So L plus y. Therefore, here in this third picture, the restoring force must be F2 is equal to minus K times L plus y. So L is called extension and y is called the vertical displacement. So here L is actually called as extension and y is called as the vertical displacement along the y-axis. That is in the vertical direction. So now I will write an expression for the net force in the third picture. So in the third picture now, mg minus k times L plus y is equal to m into acceleration a. So first I will write acceleration is the second derivative of the displacement d square y by dt square. So y is the displacement, dy by dt is the first derivative of the displacement, that is called the velocity, and d square y by dt square is the second derivative of this displacement, and that only is called as the acceleration. So in place of d square y by dt square, I can also substitute m into a, is it not? That is mass into acceleration. Now I will expand this. First term is mg minus second term is k into l. Okay, so this is minus kl. And the third term is minus k into y. So this is minus ky. And that is equal to m into a. Okay, children. Now from the previous step, what is mg is also equal to kl, is it not? Mg in magnitude. In magnitude, the force mg is also equal to the force kl. So here mg minus kl is there. In place of this mg, I can substitute now kl. From here, instead of mg, I have substituted. So kl minus ky is equal to m into a. So this kl and minus kl get cancelled. So minus k times y is equal to m into a. I will change the sides. Okay. Or I can write now m into a is equal to minus k into y. Again, what is acceleration? A is equal to minus k by m into y. So this is the second equation. I well understood how we derived the second equation. Okay, from the definition of SHM, okay, from the definition of SHM, the acceleration must be equal to minus omega square times y, is it not? So this is A is equal to minus omega square times y, because we have defined SHM as a type of motion in which the acceleration of a body is directly proportional to the displacement, okay, but oppositely directed, is it not? That is why minus omega square times y. So look at the equations 2 and 3. Their left hand sides are same. So I am going to equate the right hand sides. So from equations 2 and 3, I can write omega square y, okay, minus omega square into y is equal to minus k by m into y, minus k by m into y. So this minus and y term get cancelled. Okay, minus and y term gets cancelled. Therefore, omega square is equal to k by m. Okay. Therefore, what is omega equal to? Therefore, omega, okay, is equal to square root of k by m. Omega is equal to square root of k by m. So, after this, we can apply this in the expressions for a period of oscillation and frequency. Very simple. Okay. Now, period of oscillation is given by capital T. So, capital T is equal to 2 pi by omega. So, this is equal to 2 pi divided by omega is what? Square root of k by m. So, this is equal to 2 pi into square root of m by k. Understand? The similar equation or the same equation only we have got just in the previous video for the horizontal oscillation, linear harmonic oscillator. Understand? So, now from the previous equation, what is m by k also is equal to L by G. Is it not? Here what do we get inside the square root is what? M by k. So, instead of root m by k, we can also substitute root L by G. Therefore, now T is equal to 2 pi into square root of L by G. So, this is the equation similar to that of a simple pendulum. Understand? The simple pendulum, the horizontal loaded spring and the vertical oscillations of a spring all are alike, okay, unique in nature. So, the oscillations are similar, okay. So, now this will be called as equation number 4. What next is we have to derive an expression for the frequency. So, frequency of oscillation is defined as the number of oscillations produced per second, and it is numerically equal to the reciprocal of the time period. So, frequency is f is equal to nu equal to or n equal to 1 by t. So, this is equal to 1 by 2 pi into square root of k by m. This is one form. You can use f or the symbol nu or the symbol n for frequency as you like. Okay. So, we will write therefore f is now equal to 1 by 2 pi. The reciprocal of root L by G is root G by L. Okay. So, this is now equal to root G by L. Okay. So, the final equation is numbered as 5. Okay children, the fifth equation I have understood. I will just recapitulate what I told. In the case of a vertical spring, when no load is attached, it will be permanently at rest. Okay. What will happen when a load is attached to the free end of the spring? Just it will be stretched, that's all. It will not oscillate. Just the bottom end of the spring will be stretched down. Understand? So, from the center of this load, from the center of gravity of this load to its previous position, if you measure, that is called extension of the spring, and its symbol is L. So, it is now in equilibrium, static equilibrium. It is at rest. So, the acceleration of this system is equal to 0. So, the net force must be equal to 0. So, what are the forces acting on it? Mg acting downwards and minus KL, that is in the upward direction, called the restoring force. So, Mg minus KL is equal to 0. So, in the third picture, we pull the load downward and leave it, so that now only the system is oscillating. So, in the third picture, the net force is now not equal to 0, is it not? So, here there is some acceleration of the system and from there we have calculated the acceleration of the system, and we have got an expression for the angular frequency omega, and then we substituted in the expression for the time period of oscillation and the frequency of oscillation. I hope you must have understood well. Fine.